Hi, everybody. Thank you so much, Mirai, for this nice introduction. It's a great pleasure to me to be with you today here. And thank you so much for the organizers for organizing this and sending us this invitation. Okay, as was already introduced by Mirai, our aim is to give you a certain overview of application of artificial intelligence in food safety. I am Yamine Bouzembrak. I work now in Wageningen Food Safety Research, which is part of Wageningen University and Research in the Netherlands. And I do what we do. Our mission really is application of artificial intelligence in food safety to keep food really safe. I do this work with these nice colleagues, Anand, Minjin, Leonika, Lucas, and Wouter and Hans. And it's really thanks to them that the things that I'm going to present for you today and share with you today are happening. Next. We prepared this structure for this presentation. I will start with a short introduction where I will give you an overview about what is happening in our field in food safety and big data and artificial intelligence in these 5 last years from 2015 to 2020. Then from there, we were thinking which interesting case that we can share with you and discuss with you. And we came up with these 2 cases. The first one is artificial intelligence and system approach in food safety, where we applied the Bayesian network to predict food fraud. And the second one is using NLPs and text mining in food safety, where we managed to identify new stimulants in food safety that our experts are following now. And we will conclude with what we learned from these 2 cases and where we are going. Yeah, as I mentioned, I hope you can see it well because I don't see it very well here. Yes, I thought I can share with you this nice figure that we published last year in December, where we did the literature review on what is happening in food safety in big data and artificial intelligence from 2015 to 2020. And we found 113 relevant article. And this figure shows the co-occurrence network visualization of the abstract and the titles. This means we wanted here to really show you, let's say, the summary of all the abstracts of all these papers and the titles. I will try to read it now because it's okay. You see in the network, you have 4 big categories or groups. They are here in colors. The circles are the terms that you have in the abstract and the titles, and more the circle is big and it was more frequently mentioned. I mean, if I go to the red category, it says like applications, platforms, and technology, which is more the technology part, where you will find here in this part, for instance, blockchain, traceability, artificial intelligence, sensing, and etc. I am not reading it, but I just using my mind now. Then if I go to the green part, it's system approach, system models, food fraud and approaches, let's say, and all Bayesian network and the approaches used in this area with the system approach. Another group was this yellow one, which is related more to risk assessment, where you have data, guidance, strategy, data decision making. It's like more policy related to food safety. And the blue group one is more food safety issues, food safety, big data, and what was it, this one? Yeah, something like sensors and cloud computing. I wanted to zoom in in the next slide. You will see more the approaches that you can find more. In this figure, it's like a zooming in just in 38 articles from this set of relevant articles where we wanted to dig in which approaches are used nowadays in food safety. And you will find here in the blue cloud or the blue group, you have systems that are using video analysis and sensors and artificial intelligence to deal with food safety. Then here in the green part, it's basically data mining and text mining in food fraud using GraphF and stuff like that. And the red part here is food safety issues and food safety analysis using text mining and text analysis and network analysis. I will just skip it then now. If you need then nicer figures and more details about what I told you now, just check our latest publication. In short, let's say like a conclusion, the research in AI and big data in food safety is still really in its infancy, but there is a huge increase just in this last 2 years in that sense. Let's start with our first case. About artificial intelligence and system approach that we developed in food safety. And for this case is specifically what we did with the food fraud case. To predict food safety, you need really, it's a big issue in that sense. Food safety issues are driven by many factors or drivers that we call them that are interacted directly or indirectly. And you can see here, your food generally, it goes through the full chain from farm to fork that you need to understand all the steps in the chain, what is happening in the chain. You need also like to add into your models an expert knowledge. They know what is happening there and to include their knowledge. And you have also the knowledge from the data, which is generally very big data to include from all these drivers that can affect the food safety issue that you are trying to predict or you are trying to monitor. That's why it requires really a system approach. And when I say system approach in short, just saying, take everything in the chain is interconnected, and we should look at things as a whole rather than just a group of independent parts. It means looking to the big picture first, then digging in deep to examine its part and focusing on relationship between them, which is, and these elements of a system approach, we found them in one of ML approaches, which is a Bayesian network approach. We had this question why Bayesian networks many times. That's why I want in short to clarify it for you. Bayesian network is a family that belongs to probabilistic graphical models. It combines different theories. Like you have a graph theory inside it, you have probabilistic theory inside it, and you need some skills in computer science and statistics. In food safety, why we went to BN in a system approach, it's like it contains all the elements of system approach. You have your components, which are your drivers and factors. You have the interactions between the all factors, and also you can play what if scenarios with it. It's like if you have a question about in future, what will happen if this parameter, knowing this evidence and this and this and this, you can play it easily and even show it for your stakeholders or your partners and your experts. BN, comparing to other machine learning like neural network, is you can explain it. It's transparent approach comparing to the more complex ML algorithms. And it takes into consideration also numbers and the qualitative criteria. And the uncertainty also is involved in the parameters, which is in food safety very, very important for us, especially explaining it and taking into consideration all these factors together. We applied it in several chains, let's say food chains, like we used it successfully to predict food fraud. in this model here, and we use it also to predict fruit and vegetables, including climate, let's say, you give us like the conditions in the origin country, what are the climate, what are the economical factors, and can we predict the most likely food safety hazard that could occur before you check. And we use it also in nanoparticles in Safe by Design, giving the properties of your nanoparticles, the chemical properties and physical properties before you start analyzing or doing experiments with your nanoparticle. You can assess with high accuracy which effect will have in human health. And we applied it also in different other chains like spices and herbs, and also in milk and in dairy chain, and even in other feed applications. I will focus now. Steps of food fraud generally. To build a Bayesian network, you have 4 major steps that we take into consideration. Is factor identification, the first one. Then from there, you need to define like data sources from where you need to collect the data and collect the data related to it. Then you start building your model and validating it. And it's like a circle. It depends on your accuracy. Then you can add more data or define other parameters and so on until you get a certain level of accuracy that you are happy with it. If I go to the first one, which is identification of the parameters, to identify the potential drivers of food fraud, we use literature and expert elicitation, like in brainstorming sessions. And those experts, they gave us a set of factors to include in our model. Here I have 2 big drivers as examples. If I take the economic factors, you have the price of the product, the price if there is a price spike in that period, and the trade volume and the complexity of the chain. There is also factors related to origin country and the country who is checking, or the detection country. We have factors like corruption index, food safety index, governance index, legal system index, human development index, and many other factors. Then, of course, you need to collect and process the data. Or do I have another slide, I think, before? Oh. Okay. Then we collected we used 2 databases to collect the food fraud incidents, because to build the model or machine learning model, you need the historical data. And the historical data related to food fraud, we collected all food fraud notification reported in RASEF. And RASEF is the Rapid Alert System for food and feed, which is basically, it contains notification related to food fraud, and you can call it even a European food fraud database. And we used also EMA, which is Economical Motivated Adulteration Incident Database, which is an American one. We collected all the cases from 2000 to 2020. And for each food fraud case in this data, you need to link it to all these factors identified by the expert, like let's say the indexes for corruption index, and all the factors identified by expert and literature will be linked per case. We use then part of it to, we ended with linking 36 factors, as you can see here, from 18 data sources and 8 expert judgment. And expert judgment in factors where there is no data, in the sense Is it complex to detect this type of fraud in this product? Then the expert who will give a value saying if it's low or high or medium. And another case also, like, is there a technique to detect this type of fraud in this commodity? Then the expert who will judge for each case, give a value or an estimate. Of course, classically, we divided then our data set to training data set and the validation data set. 83% of the total data set were used to build the structure of the BN network and to train the parameters of the model. And which algorithm used was the TAN BN for this case, and using a completely independent data set to check the accuracy of the model, we ended up with a very high accuracy of prediction of type of fraud for this case. How BN looks like? It looks like this. You have all these elements, or the ellipses are the names of your factors. And from with different colors, which is the colors again is the categories or the groups. If I go to the green ones, is the economical ones. Here it says like the price, I think, and this is the volume, price per month, and the other economical factors. And you have your interactions here, and the rectangles that you have here, which is almost the distribution of your parameter, which is a discretized distribution. And the green part here is like also the probability. More high you have it, it's really like a distribution here. I cannot give you more information since the picture is not that clear now. I will just move in now to the next slide. Yeah. After building the model, the question that came up to us was how to make the system automatic, in the sense how to collect this data in real time, how to process it in real time, how to update our even model with the new data in real time. So what we did, we used Mime to develop workflows to automatically collect and process data from all these data sources to predict food fraud. Inside of each workflow for each indicator, this is like your data sources, let's say Medicis, RASEF, Eurostat. You acquire the data, you clean it up, then after cleaning it, cleaning the data, you structure the data, and then you build your Bayesian network and the process and run the model every time that you have new data. And what we had for our experts also, they see nothing from the Bayesian network. They have a dashboard built in Kibana to just see the results and collect the data in very nice dashboard. And all this system is running in the cloud infrastructure of the high performance computer of Wageningen University. I have an example for the price ingredient, for instance, from Eurostat. If you will do the work manually, you need to go through all these steps for each product and for each country. And using Mime, it becomes just a workflow that you need to plug in to a certain URL, and there is a loop automatically to extract that data from the data source and structure it as you like it. And you can imagine now you have for each data source or for each parameter in your model, such kind of workflow to do the work for you. What our experts see is just this dashboard where they can, let's say, query or run scenarios or analyze the data. They can select the product, the origin country. They can select, play all scenarios that they would like. You can see here the output of your Bayesian network. This is a cloud world of the origin data. You can select which country you are interested. Just in China, you click in China, and the dashboard in very dynamic, it becomes just analyzing the data of China and all the figures related to that will be updated automatically. And what can the expert also have is download all the data in CSV format, ready to use for any machine learning exercise. Yeah, for more information about the system approach used in food safety, we have the latest publication. This one, it was in 2020. And we have another one also that I recommend to you if you would like to read about this expert-driven methodology that we developed for the EFSA, European Food Authority, in the way how to select really the right factors for any question in a systematic way, which combines like literature, expert, Delphi studies. It's a very, very nice way to select and define your parameters in any ML problem, I think. I think this is it for the first case. I will move now to NLPs and text mining in food safety, and our case of finding new stimulants for our expert in WFSR. In short, I will give you like a short definition of a stimulant. What is a stimulant? A stimulant, it's a drug that produces a temporary increase of the functionality, activities, or efficiency of an organism or any of its parts. It can be used to treat obesity, to increase focus, to decrease appetite, to decrease need for sleep, and etc. And the problem with the stimulants in food safety, there is always illegal compounds are sold as food supplements, and sometimes you don't know even in the supplement the ingredient inside. Then the food authorities should know them and check them if they are really fitting to the legislation. It can lead to health problems also to the consumers. And what we wanted to do, now the questions that we wanted to address in this is using artificial intelligence to find other compounds that should be added in the monitoring. In that sense, we have a set of stimulants that we are checking every year, and we would like to update that list automatically or systematically in a scientific way. And what is being used also in the market, because the market is moving and things are changing, and other compounds which we are not aware of. And how we did this, we came up with this approach, which has four big pillars. The first one, and the four big pillars in the sense, four different data sources. We use social media like Twitter to collect all the stimulants tweets, and we use sentiment analysis and some text mining. And from there, you came up with a potential set of emerging stimulants for the expert. Then the EMM, like another data sources, and EMM is a European media monitor that collects all what is happening in the web and the internet in the media, like an information. I will give you more details about it later. And we used some machine learning techniques to extract knowledge from there also, and to come up with a second potential set of new stimulants for our expert. We mined also EuroPMC, which is the biggest scientific literature database with synonyms, and the same for the stimulants. And we used word embedding to extract knowledge from there, from literature, and find another set of emerging list stimulants that the expert will check. And we used also the rapid alert system for food and feed to collect the notification related to stimulants. And this one is not used to get the new ones, but it's like to show to our expert if there is an increase in use of one of them. Yeah, I will start with the scientific literature. Not this coming. Okay, as I mentioned already, the aim is to find new stimulants in scientific literature that are currently not yet mentioned. not yet monitored, sorry, using artificial intelligence. We used Europe PMC as our source of literature because it provides a single point for access to the abstract through PubMed and PMC and even more than that, more than 5 million other sources, including synonyms from chemical databases. All scientific literature that contained one or more of the 428 compounds or their synonyms in the title and abstract was collected. We used the literature from 1990 to 2019. This yielded in approximately 2.1 million articles to analyze. And using this 2.1 million articles, we built a word embedding model based on the text of the title and the abstract. What is a word embedding model? In words, word embedding is an AI technique used to identify words that occur in the same textual context. And embedding is just a word represented in a high-dimensional vector of numbers. A word embedding model is a model that converts a word into a numerical vector based on all other words in the data set. Instead, it converts your text to really a space of vectors. Good word embedding model preserve semantic relationships and syntactical relationships with other words. Related words are closer together in the same vector space, and it allows for relational mathematics. Like here, male, female example, you have male here, and this is male of men and woman maybe. Then you have queen and king related to each other, verbs, verbs, time also in the tense in that sense, and here country and capitals example. For each country, you will find the capital name close to it, for example. We used word-to-vector word embedding neural network. The model can be used to find words that are similar to or occur together with a targeted word because they are used in the same context. For example, if there is two sentences like I need some caffeine to keep me awake, I need some coffee to keep me awake, these two words will be put in together. This approach can help research in identifying new elements within a topic, which in our case is the stimulant one, and it can be scaled up to any other case or applications. Then from the word embedding model, what we did, we wanted to know the closest words to the stimulant word, and we saved only the words that were chemical compounds. Then from that set, we took out the original 428 list, the original one and their synonyms, we removed them. We ended up with the top 50 compounds checked for their validity. This resulted in 15 new stimulants, completely a new one. What we did with these 15 new stimulants, we checked them with our expert in this domain. And this is the result. He said 5 compounds were considered completely new and relevant for him, and 5 compounds were considered new also, but the molecular formula was already present in the database. Then he added them. 3 compounds were considered stimulant, but not relevant for the food supplements, but relevant for food in general. And 2 compounds were already present in the database, but not specifically indicated as stimulants. The pros and the cons of our word embedding model is The pros are time efficiency, topic independent, can be updated continuously with new literature, and it's an unsupervised learning approach. There is no labeling required to do. Limitations, of course, is the data that you are using. It depends if you are getting the right data or not. Limited scope of knowledge. We are analyzing just the title and the abstract, and lacking meaning behind words also. It's the sense you have to try always to understand what you get out from the model. Now, what I presented in the first pillar was using word embedding to get a new stimulant from scientific literature, mining 2.1 million articles. And we found from there 12 completely new stimulants. And now we will go to using text mining to mine the media, what is happening in the web. Yeah, detecting new stimulants from media. What we use there by screening media and blogs worldwide. And which system we use to do that, which is the EMM, which is the European Media Monitor. EMM applies text mining techniques to screen different types of media in the world web, like website, database, blogs, and everything news in the media, what is in the 3W. EMM is updated every 10 minutes. It works 24 hours, 24/7, and gathers reports from new portals worldwide in more than 60 languages. It has 3 portals, and the portal that we used was the last one, Medicis system, because our topic is related to the medical area and health. And Medicis is completely open access for everyone. If you just type Medicis, you will get into the original page. And the system is hosted by the GRC, Joint Research Center, and is used also by the European Food Safety. And we are one of the institutes that has access to this system to personalize it to any topic. And the problem there, you have these filters built up by the GRC and the EFSA, but there is nothing related to stimulants. Then we created a new filter that helps to collect and gather, centralize all the information related to stimulants. How we did that, we used exactly the same approach that we used in the collection of the literature articles, used the set of the monitoring chemical names and their synonyms, and we put them in the system. And now the system is collecting stimulants publication worldwide. And generally here it gives you like an abstract of the paper and the title of the paper. Just you click on the link and you go directly to the origin source of the publication that you can read. Yeah, and here's some examples of the recent publications. Then from there, we had the problem of the EMM system is just it collects just the publication, but after a few weeks, they disappear from the system. There is no storage system, and it's not. They cannot save it in their system. This is how it was designed by GRC. Then for us, again, the question of automation and making it useful for us, like in a database for our scientists, it was a new challenge for us. That's why, as we said, EMM collects from papers, blogs, databases, websites. Then there is an automation work that we did here. Automatically retrieve this information from EMM, store it, and process it in a real database. And process it and even visualization of the output in a nice dashboard. And now this is what our expert can see. Is an online real-time visualization of the collected report. They can analyze them by chemicals in real time per country, and even they can download them and click and read them if they would like. And the result of the second exercise from EMM, we found 12 compounds were considered new stimulants relevant for the database. Here I have some examples of interesting findings. Let's say this was found in September 2020, where it says DMAA is one of the stimulants. It's a biological activity. They use it for, I think, to increase using available to increase. But the problem on it was the ingredient may be particularly dangerous when it's used with caffeine. This one was reported systematically to the Food Authority. One of the other ones, completely new ones, 5 new stimulants published in literature. We get them, the system got them and sent to the Food Authority also. Another one, it says, you can lose weight. You can lose weight while sleeping. You don't need to exercise. You don't need to follow any diet. In that sense, it's magical. And the problem again is this stimulant, it wasn't tested on any human or any animal, and there's any evidence that, and it was sold in the market. And when this one was October 2020, when the system got this publication like an alert, it was available in the Netherlands online to sell for the consumers. Yeah, all these applications that I showed you, there are, we have now in WFSR big data infrastructure for artificial intelligence applications, and all our scientists have, like in few clicks, access to different applications in different domains. And yeah, this is what we basically did. And now I am for my last slide. Yes, what we learned from these 2 cases, research in AI and big data in food safety still is in its infancy, and it's grown very fast and quickly. AI and system approach in food safety and automation of data retrieval and processing in real time is being developed. And results are really encouraging and encouraging us to go to the next step and get more automation on this area. Successfully managed to detect unknown stimulants for our experts from literature and different data sources, and the system can be scaled up to any other topics for food safety hazards and product. And for the moment, we are busy implementing the same system for the Food Authority for getting and detecting supplements and any other hazards. You need big data infrastructure and in food safety, basically, and acceptable data governance, which is the problem of sharing data and confidentiality of data, especially in food safety again. All these issues should be taken into consideration. The security, the ownership are really big topics, I think, that needs to be discussed in food safety regards to AI and big data. The other things we are, the next steps, we are busy. I think just for this year, starting of the year, we have more than 20 AI projects where we have computer vision, reinforcement learning, predictions of food safety using different ML techniques. Mirai, I think this is my last slide. Apologize for the quality of the slide. We didn't expect that personally.
Okay, thanks, Yamine, for your presentations. I have a few questions on the Q&A things. So the first one is from Elena Mikosi. Can you define food fraud? Do you have examples?
Yes, thank you, Mira, for the nice question, and thank you for asking this question. Yeah, food fraud. What is food fraud? Food fraud is everything that you add to your product, to your food, for aiming to have a gain, an economical gain. Let's say you add water to the milk in addition to a gain, let's say, to sell more and to gain more money, which is illegal, but for the guy who is frauding is to get more money. They add to, let's say, any food commodity like spices and herbs. They can add or substitute other cheaper ingredients in addition to knowing they would keep the same quality of the product. You don't feel it, but inside it's not the right product they bought. You bought, or they claim they are selling a fresh product, but it's not a fresh product because the fresh one is more expensive than the frozen one, for instance. You can fraud in labeling also. You say, I am saying organic or olive oil, but really inside is not organic olive oil. Or you say, this is an olive oil imported from Italy, but really is not imported from Italy, but maybe it's imported from Africa, just to get the labels and gaining money again. There is a lot of types of food fraud. You can fraud with labeling, you can fraud with substitution, you can fraud with artificial ingredients, you can fraud with documents, you can fraud,
Thanks.
I hope I answered the question.
Thanks, Yamine. We have two questions now from Dina Gergis. I apologize if I mispronounce the name. She asked why 83% of the data was used to construct the tree. Any reason why it is exactly 83%? So I think it's from the Bayesian network she's talking about.
Yes, there is no reason about it. Thank you so much for your nice question. It was just used for years. That's in the sense also when we build the Bayesian network, we do generally a splitting of 20/80, but for this one specifically, it was related to years. We built it till 2016, and the remaining ones were used completely like new data set for the future, knowing it's this data, we didn't use it there, and it was there for us in mind, it was 2080, but it was 83, then we used it like it was there. But generally, we use it even more, 2080, building, validation, and we use completely a new set to an extra test.
Okay. And I have another one. Any reasons why you choose MongoDB for the natural language processing?
A very good question. It's unstructured data. That's the main reason. Which is no SQL data in that sense. It's not a relational database. And we use only open access. We don't buy any software. All the things that we have in our WFSR infrastructure is open access and available for anyone. We don't buy anything. So we use MongoDB, we are using Elasticsearch, we are using Kibana. All the things that I showed you are in open access for everyone. But basically in the beginning was because we were collecting JSON files and unstructured files.
Okay, and I have a last one from Nicola Colombo. And okay, it's a long one. Do you think this research can be considered an early stage toward common sense reasoning? I mean, will it ever be possible to have machine find correlation cause of a food risk? And to give an example, let's say there is a RAS report related to PFAS contaminations, and another document talk about using plasticizer in food equipments. Can the two documents be correlated to infer that the potential risk comes from food equipments? So it's quite a tough one.
Yeah, it's a really tough one, a really good one. I'm just thinking how to answer it in that sense. It's a complex question. Really, I don't know the content, but of course, it can. No, I cannot say yes or no. This is I don't have all the ingredients to say yes or no. But what I can say, my conclusion: look, if you want to go for word embedding, it depends what you want to build with it, and it depends what you want to analyze with it. But it's a really powerful system to find. Look, there is no scientist who can read 2.1 million articles, whatever you are. If there is a machine that can help you to screen them quickly, find chemicals that you are not checking or finding semantics that you are interested in, finding matchings between words or even database. You can use it to link different data sources, as you mentioned, maybe RSF in another database. Yes, if your aim is to do that, it's not just word embedding, but you can use text mining. We have such kind of project already where, but there it depends also in the complexity. In the case which I'm talking about, we are building an ontology because I need to link RSF database to FAO to Eurostat, and the words used in these different databases are completely different. Then you can use like word embedding to help you to link, to find like matching. And we did it already, and it was like even around 80% helping you to match RSF to FAO Stat, for instance, and another databases. And you can use in between other techniques and like neural networks to do a certain part on your aim. But finding one who will do everything on matching, that's really tough. And if you know it, please, you know my email.
Thanks a lot, Yamine, for this last answer. I think overall it was a very interesting talk to see a little bit what's going on. And we see there is a lot of things already done, but also still a lot of things to be done on food safety and artificial intelligence. So thanks a lot. We will have a short break now. And we come back in 5 minutes for the next talk.
Thank you so much, Mirai, and thank you so much for the whole team, especially the guys who were close to me, Mirai, Hugo, and Pauline. Thank you so much.